Welcome to Signal Ahead. I'm Alfred. Today's briefing, quantum computing. Sunday, August the 02. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. There's a word that keeps surfacing this season, and it isn't supremacy, and it isn't even advantage, though that one is doing a great deal of heavy lifting in the press. The word is verified. And if you were skimming the headlines this week, you'd be forgiven for missing why that single, unglamorous adjective is the most important thing to happen to quantum computing in some years. Here is the non-obvious insight I'd ask you to hold on to. For the better part of a decade, the great problem of this field was performance. Could a quantum machine do something a classical supercomputer cannot? But quietly, the problem has shifted. The bottleneck is no longer whether the machine can outrun classical computation. It's whether anyone can trust the answer when it does. And those are not the same problem at all. In fact, they pull in opposite directions. The moment your quantum computer solves something a classical machine cannot simulate, you have, by definition, lost your ability to check its work the old way. There's no answer key. The very achievement that makes the result valuable is the thing that makes it unverifiable. So when we hear this week that IBM, working with researchers at the University of Chicago and a couple of quantum software startups, claims to have demonstrated quantum advantage, the striking part is not the advantage itself. Earlier demonstrations leaned on contrived problems, sampling tasks engineered to be hard for classical machines but bearing little resemblance to anything you'd actually want computed. And they leaned on statistical arguments, on strong assumptions about how the hardware would behave. What's new here is the insistence that the results are correct and can be shown to be correct, despite the fact that no classical machine can reproduce them. 3 demonstrations, paired with 3 ways of validating the output. That is a subtle but profound change of ambition. The field is growing up. And growing up means learning to be checked. I want you to notice how deeply this theme of trust runs through everything else on the table right now, because it's not confined to one company's press briefing. Think about the perennial software question: why software projects fail, a subject that has occupied risk analysts for decades. The lesson there was never that computers can't compute. It was that we build systems whose behavior we cannot fully anticipate, and then we deploy them into the world and are surprised when they betray us. Quantum computing is now stepping onto exactly that terrain, only with higher stakes. Because you cannot debug an answer, you cannot independently produce. And that reframing helps explain a great deal of what otherwise looks like a scattered, noisy field. Consider the move toward vertical integration. A trapped ion company buying an American semiconductor foundry, taking ownership of design, fabrication, packaging, and deployment, all under one roof. On the surface, that's a business story. But underneath, it's about control in the fullest sense. If you own the entire stack, you can account for the sources of error. And accounting for error is the precondition of trust. Consider the silicon spin processor demonstrated to run autonomously with a cryogenic control chip, replacing racks of room-temperature instruments. Again, that's not merely about elegance or space. Every wire you remove is a variable you no longer have to reason about. Every layer you fold inward is a place where noise can no longer hide. And consider the quieter, less heralded work, the study suggesting that a noncommutative form of quantum error-correcting code might be both more powerful and more stable than the alternative. Error correction is the deep machinery beneath all of this. It is, in the end, the same preoccupation wearing different clothes. How do we know the machine did what we think it did? The field has spent years chasing raw capability, and it is now, all at once, turning to the harder and less photogenic question of reliability. So where does that leave us? As an honest assessment of where the domain stands, we are watching a discipline pivot from the theatrical to the accountable. The demonstrations that matter now are the ones that come with proof. The partnerships that matter, a rail operator scheduling its rolling stock, a clinic predicting which tumor mutations the immune system will notice, are the ones testing whether quantum methods survive contact with messy, real-world data, where there is no toy problem to hide behind. And the money, whether it's national materials initiatives or a consulting giant installing a machine on its own premises, is increasingly betting on integration and infrastructure rather than on a single breakthrough moment. Over the next 2 segments, I want to follow that pivot down 2 roads. First, into the hardware itself, the qubits, the photons, the strange materials that only reveal their magnetism under strain, to ask what it actually takes to build a machine you can believe. And second, into the uncomfortable question of what we do with results no human can check. Because a technology that produces trustworthy answers we cannot verify is not merely a new tool, it is a new kind of authority. And we should decide, rather deliberately, how much of it we intend to grant. There is a moment in the life of any technology when the story it tells about itself changes shape. For years, quantum computing has lived on a single sentence, the promise that one day a machine will do what no classical computer can. That promise has been a kind of horizon, always visible, never quite reached. And the temptation, when reading a week's worth of announcements, is to treat everything through that lens. Has the horizon arrived or hasn't it? Did someone cross the line or didn't they? But I want to suggest that the line itself is no longer the interesting thing. Beneath the headlines about advantage, and there were several this week, all clustered around demonstrations that a quantum machine had performed a computation beyond the practical reach of classical simulation. Something subtler and, I think, more consequential is happening. The deep current is not about speed. It is about trust. Consider the problem those demonstrations were actually solving. For decades, the awkward truth of quantum advantage has been this. If a quantum computer solves a problem that no classical computer can solve, then no classical computer can check its answer. You are left holding a result you cannot verify, produced by a machine you cannot fully model, under conditions of noise you cannot entirely characterize. The claim of superiority contains, in its own logic, the seed of doubt. And so the meaningful advance this week was not merely that a machine ran a hard computation. It was that the researchers brought along methods to validate the result, to establish that the answer was correct despite being impossible to reproduce classically. That shift from raw performance to trusted performance is the deep current. The field is quietly ceasing to ask, can it go fast? And beginning to ask, can we believe it? You see the same current running through the error correction work. There was a study exploring a less traveled family of quantum codes, the noncommutative kind, where the order of operations matters, with the suggestion that they might prove both more powerful and more stable than the more familiar alternatives. Notice what is being optimized for there. Not speed, stability, the unglamorous virtue of a machine that does not lie to you as it drifts. Error correction is, at bottom, an engineering of trust, a way of taking components that are individually untrustworthy and weaving them into a whole you can stake a calculation on. And it runs, too, through the architecture. A silicon processor that governs itself, its control logic moved down into the cold, no longer dependent on a tangle of room-temperature instruments issuing real-time commands. Independent efforts wrestling with how to wire up vast numbers of qubits without drowning in cabling, how to connect qubits that do not sit conveniently side by side. These are not the announcements that make headlines, because they are not about breaking a record. They are about building a thing that can be relied upon at scale, a system whose behavior you can predict, whose errors you can bound, whose outputs you can trust enough to plug into something real. Which brings me to the other half of the current, and it flows in the same direction. Alongside the physics, the week was full of quiet acts of institutional commitment. A rail operator running a scheduling problem, assigning physical train units to timetables on real operational data, not a toy. A professional services firm installing a machine on its own premises as part of a far larger technology bet. A trapped ion company completing the purchase of a semiconductor foundry, folding chip fabrication into its own house. That last move is telling. Vertical integration, owning the design, the wafer, the packaging, the system, is what a field does when it stops treating hardware as an experiment and starts treating it as a product. You do not buy a foundry to run a demonstration. You buy a foundry because you intend to ship. So the deep current, if I have read it rightly, is a convergence. On one side, the physics maturing from spectacle into verification, from "look what it did" to "here is why you can believe it." On the other, the institutions moving from curiosity into infrastructure, from press releases into railway timetables, from rented cloud access into machines bolted to the floor and foundries brought in-house. These two movements are the same movement seen from different rooms. Both are about the crossing of a threshold that has nothing to do with any single benchmark. It is the threshold of dependence, the point at which people begin to build things that assume the technology will be there and be right. That is a quieter milestone than quantum advantage, and it will never be declared on a single Tuesday. But it is the one that actually changes the world. A technology becomes real, not when it first outruns its rivals, but when someone else's plans begin to lean on it. And that leaning, this week, was audible. There's a moment in the life of any technology when the argument stops being about whether it works and starts being about what it will mean. And I think, having spent our previous conversations picking apart the machinery, the qubits, the error correction, the strained oxides and diamond defects, we've arrived precisely at that threshold. So let us ask the harder question. Not can it compute, but what happens next once we grant that it can. Consider first the matter of trust, because it turns out to be the quiet hinge on which everything else swings. The recent demonstrations of quantum advantage carried a peculiar burden. It is one thing to build a machine that outperforms every classical supercomputer on Earth. It is quite another to prove that it did so correctly, when there is, by definition, no classical computer available to check its homework. This is a genuinely strange epistemic position. The whole enterprise of science has rested, for 4 centuries, on the ability to verify a result independently. And here we have machines whose entire value proposition is that their answers cannot be independently reproduced by the older methods. The engineers involved understood this, which is why the interesting work was not merely the computation, but the validation techniques wrapped around it, the mathematical scaffolding that lets you believe an answer you cannot recompute. Watch that space closely, because I suspect the second-order implication is this. In a world of unverifiable computation, trust becomes an infrastructure. Not a feeling, not a reputation, but an engineered layer with its own standards, its own failure modes, its own vocabulary. We spent decades learning why software fails. The accumulated wisdom of the risk ecologists who catalogued 1,000 debacles. Quantum computing inherits all of that and adds a new wrinkle, software that fails silently in ways no ordinary test can expose. The discipline that grows up around proving quantum results correct may end up mattering as much as the hardware itself. Now turn to a different signal, easy to overlook. A trapped ion company purchases a semiconductor foundry. On the surface, a corporate transaction. Underneath, a thesis about the future. Vertical integration, owning design, fabrication, packaging, and deployment is what an industry does when it decides the era of borrowing components from adjacent fields is over, and the era of building a native supply chain has begun. The same instinct appears when a professional services firm installs its own machine on-site, rather than renting time in the cloud, or when a national laboratory aligns its research to a formal executive directive. These are not experiments anymore. These are institutions committing capital and floor space and organizational identity. The tell is always the same. When the plumbing gets built, the party is real. But here is the subtlety I want you to hold on to. The most consequential quantum results this season were not, I'd argue, the advantage demonstrations at all. They were the quieter ones. A silicon processor that runs itself, its control electronics folded down into a cryogenic chip rather than sprawling across racks of room-temperature equipment. 2 studies pushing spin qubits toward the scales where wiring stops being a bottleneck. A memory device squeezed to the single electron limit. These are engineering victories, and engineering victories are what actually change the world, because they attack the unglamorous constraints, heat, wiring, control, cost, that separate a laboratory curiosity from a manufacturable product. The headline says, "Advantage. The future is written in the footnotes about self-running control chips." And then there is the widening. Notice how many of these efforts point outward, toward connection. Photons made indistinguishable across utterly dissimilar hardware, a warm cesium vapor and a semiconductor quantum dot persuaded to speak the same optical language. Light's hidden twist protecting information through bad weather. These are the beginnings of a network, and a network changes the second-order calculus entirely. A single powerful machine is a tool. A web of machines that can pass quantum states between them is something closer to an ecosystem, with all the emergent behavior and vulnerability that word implies. So what should you watch for as this argument unfolds beyond us? Watch whether trust becomes standardized, whether validation moves from bespoke academic effort to routine industrial practice. Watch whether the supply chain consolidates, because consolidation signals conviction. Watch the footnotes, not the press releases, for the boring engineering that removes real constraints. And watch the interconnects, because the moment these machines learn to talk to one another reliably, the story stops being about individual devices and becomes about a fabric. The temptation, always, is to ask when quantum computing will arrive, as though there were a ribbon to cut. But technologies of this magnitude do not arrive. They accrete. They become load-bearing before anyone announces it. The question worth carrying with you is not whether the machine works, but which parts of our world will quietly come to depend on it, and whether we'll have built the trust to know when it fails us. That, I think, is the signal ahead. That's the signal for today. The noise will keep coming. We'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.